Ever stop to think about how a simple on-off switch can power literally everything from your phone to a massive supercomputer? Well, today, we're going to build a computer right from the ground up. And if you're a computer science student, you'll want to pay close attention. We are about to connect all the dots between your digital logic class and that powerful processor inside the machine you're using right this second.
All right, so here's our game plan. We're going to start with the absolute most basic language of computers, and then we'll see how that language gets built into actual working circuits. From there, we'll piece together a computer's brain, look at how it thinks, and then we'll compare the two major design philosophies that shape pretty much all modern CPUs. And to wrap it all up, we'll take a peek at where processors are headed next. So, let's dive in.
You know, if you really want to build a computer from scratch, you have to start by understanding the language it speaks. And it's not English, it's not Python, it's a language that only has two words, on and off.
And that language is the binary system. When you get right down to the wires and the electricity, it's actually beautiful in its simplicity. A 0 just means a low voltage state. Think of it as off. A 1 means a high voltage state, so on. Every single thing, every piece of information from the words on your screen to your entire operating system is just a ridiculously massive string of these ones and zeros.
So, how do we actually make that binary language do something? We use these things, logic gates. You can think of them as the basic grammar of our computer's language. An AND gate, for example, will only output a 1 if both of its inputs are 1. An OR gate is a little more relaxed. It'll output a 1 if at least one input is a 1. And the NOT gate, or inverter, it's simple. It just flips whatever you give it. These super simple rules are, no joke, the foundation of all modern computation.
Okay, so now that we have these basic logic gates, we can start snapping them together, kind of like Lego bricks, to build things that can perform much more complex and, actually useful tasks.
And our first big Lego creation is what's called a combinational circuit. It takes in some number of inputs and produces some number of outputs. Now, the key thing to get here, the most important feature, is that it has zero memory. Its output is purely determined by the inputs it sees at this exact moment in time. That makes its behavior totally predictable.
And here's where it gets really cool. We can now go from simple logical rules to actual mathematics. By arranging our AND, OR, and NOT gates in just the right pattern, we can build something called a binary adder. And it does exactly what it sounds like. It takes two binary numbers as input, and it outputs their sum. We've literally just taught a collection of switches how to do arithmetic. This is a huge leap.
All right, now that we have these functional bricks, we are ready for the main event, piecing them all together into the brain of the entire operation, the central processing unit, or as you know it, the CPU.
Right at the heart of every single CPU is the arithmetic logic unit, the ALU. If you've taken a digital logic course, this diagram probably gives you flashbacks. This is the real number crunching engine of the processor. Think of it as a supercharged binary adder that can do all sorts of math and logic based on control signals it receives.
But the ALU can't do it all on its own. It's plugged into a bigger system that has registers, which are just small, incredibly fast bits of memory to hold data temporarily, and a control unit. The control unit is like the traffic cop. It decodes instructions and tells the ALU what to do. Put all these parts together, and voila, you have a complete working CPU.
This whole design, this blueprint, actually has a name, the von Neumann architecture. And it is the fundamental blueprint for pretty much every computer you have ever used. The really revolutionary idea here, from John von Neumann, was to have one single shared memory space that holds both the program's instructions and the data that the program needs to work on.
The stored program concept is the single biggest breakthrough here. See, before this, a machine's job was literally hardwired into it. If you wanted to change what it did, you had to physically rewire the whole thing. But with a stored program, the computer becomes this incredible general-purpose device. You can change it from a word processor into a video game just by loading a different program into its memory. It's a total game changer.
Okay, so we've got the blueprint for a computer brain. But how does it actually think? Let's look at the fundamental rhythm it follows, that core loop that runs every single program you use.
It's called the fetch, decode, execute cycle, and it's basically the heartbeat of the CPU. It's a simple three-step dance. First, the CPU fetches the next instruction from memory. Second, the control unit decodes that instruction to figure out what it's being asked to do. And finally, you execute. The ALU or some other part actually performs the operation. This cycle just repeats over and over, billions of times every second. Now, it turns out that when you're designing the instructions a CPU can understand, there isn't just one right way to do it. Over time, two major and kind of competing philosophies emerged about just how complex those instructions should be.
On one side, you've got RISC, which stands for Reduced Instruction Set Computer. The whole philosophy here is keep it simple. You use a small number of really basic, highly optimized instructions that can run incredibly fast. Then on the other side, you've got CISC, or Complex Instruction Set Computer. Their approach is more like, let's make the hardware do the heavy lifting by creating powerful instructions that can do several things all at once.
And you can really see the trade-offs here. RISC instructions are simple. They're uniform, and they often finish in a single clock cycle. That simplicity means the hardware itself can be simpler, leaving more room for things like on-chip registers. CISC instructions, on the other hand, are way more complex. They take multiple clock cycles, but the goal is to get more done with each individual instruction, which, back in the day, made it easier to write software for them.
For decades, the general-purpose CPU was king. It was the undisputed brain of the computer. But the kinds of problems we're trying to solve now are getting more and more specialized, and a one-size-fits-all approach isn't always the best or the fastest.
And that brings us to the specialists. The most famous one, of course, is the GPU, or Graphics Processing Unit. A CPU is a generalist. It's great at running one complex task after another. A GPU, though, is a parallel processing beast. It's built with thousands of simpler cores, all designed to do the same simple operation on massive amounts of data all at once. That's perfect for rendering graphics, and as it turns out, it's also perfect for the math behind AI and machine learning.
And this is so cool because it ties right back to our RISC versus CISC discussion. Google's Tensor Processing Units, or TPUs, are a perfect example of this hyperspecialization. They take a RISC-like approach to the extreme, stripping down the instruction set to only the commands needed for the specific matrix math that's at the heart of machine learning. The result? Mind-blowing efficiency for that one specific job.
Which leaves us with a really fascinating question to think about, especially for your future careers in tech. As we keep pushing the boundaries in fields like AI, are we moving away from the idea of a single, all-powerful CPU? Is the future of computing going to be about programming not just for one central brain, but for a whole ecosystem of these specialized processors, all working together? Something to think about.